All right, so chapter 19 is going to be on vibrations and waves. And what's kind of fun about waves is they are all around you right now as you sit here watching this video. And I don't mean that I think you're at the beach, but the waves are all around you in the form of sound that you're hearing the video, and the waves of the light waves that you can see the video. So as we look at vibration and waves, it's a phenomenon that is all around you every day of your life. All right, so let's start with vibrations, because vibrations are what start a wave. So when you look at waves, you need to start with the source. The source of the wave is a vibration. All right, and as we look at vibrations, in this case, we would have just a spring and a weight. And you can see that if it were to oscillate up and down, you can actually imagine this oscillating up and down and touching a pool of water, and it would create a wave pattern. All right, so all waves are really started with a vibration. Okay, when we look at the period of something, right? The period is the time required for a full oscillation. That's a round trip. That means there and back again. That is one period. So as the pendulum swings, the time it takes for it to go there and then back, just like that, that's one period. Whether that takes 1 second or 2 seconds, that is what we call a period. The frequency is the inverse of the period. So, for example, we were talking about the pendulum swinging in the previous slide, that it took 2 seconds to go there and back. And so the question becomes, well, how far does it go in 1 second? If we are looking at a 1 second time frame, which is often what frequency is in, it's in how far does it go, how many oscillations per second. Well, if it takes 2 seconds to go there and back, in 1 second, it can only make half a trip. It can only get halfway in 1 second. It takes 2 seconds for the complete trip there and back. It takes 2 full seconds. How far does it get in 1 second? Halfway, which in this case would be, it would travel there and it wouldn't have time to come back. So it's going to make half the trip in 1 second. And then you see our unit here at the bottom is a hertz. A hertz is one oscillation per second is 1 hertz. So hertz are really how many oscillations, how many trips per second. If it's 2 hertz, it's going to be able to make 2 oscillations, 2 trips there and back every single second. That's going to be faster. If it's 3 hertz, it can do that 3 times every single second. That's even faster. All right, now we need to talk about the amplitude of our pendulum. And the amplitude is just how far it's displaced. So we look at a neutral position, which would be hanging straight down, and how far out you pull that pendulum is the amplitude. And when we look at waves, it's going to be a similar idea. How far the displacement is going to be the amplitude of your wave. That doesn't mean how fast it's moving, it's how far it's moving. It's a displacement. All right, so let's take a look at some waves. And like I said, waves are all around you every single day. You have sound waves. Sound waves, you can hear my voice. Waves in the water. Don't we all wish we're at the beach right now? Radio waves, these are all electromagnetic waves, both radio waves, microwaves, light waves, and we'll get to those a little later in this unit. But these are all forms of waves. Now, a really simple form of a wave is just to shake a string. But it's also a very nice way to model a wave. Slinkies are also slightly more fun waves. And so we'll be doing a Slinky lab a little bit later. All right. When we look at waves, there's going to be 2 types of waves. And the first type is going to be transverse waves. And what that means is if you had a slinky or a string, you're going to shake that string up and down. But the wave is going to move left to right, all right? So the direction of the motion may be up and down, but the wave moves left to right. So let's see if I can get my little highlighter. Here we are. So the waves shake this way, all right? We're displacing this way, up and down, but the wave travels this direction, all right? And that is called a transverse wave. Okay, doing the wave. Yes, this is actually a real wave. And like a wave in the ocean, when people do the wave in a stadium, and I like the example of doing the wave in the stadium, the people don't move. They stand up in their chair and they sit back down in their chair. And like a wave in the ocean, the water molecules will move up and they move down. They don't actually travel with the wave. The same thing happens in a stadium. The people stand up, the people sit back down. They have not moved. Yeah, they moved up and down. They stood up and down. But they didn't move the direction of the wave, right? The wave travels around the stadium. You're not having people running around the stadium to make this wave. All they have to do is stand up and sit back down. And it's a transverse wave because they're going up and down, but the wave will travel around the stadium. Now we have longitudinal waves. These are different than the transverse waves in that the amplitude and the motion that starts the wave are going to be parallel to the wave. So here we go. We have a slinky. My favorite way of showing waves actually are slinkies. We're going to move the slinky back and forth, right? We're moving it this direction, and the wave travels this way. And if you look at this wave, you'll notice it doesn't wave in the traditional sense. We tend to think waves are up and down like this, right? Like a wave in the ocean. But when we look at this slinky, we realize the wave here, the wave we are sending, are areas of compression and then areas where the slinky is less compressed, right? You see this little area of compression and then an area where we have less compression over here. That is our wave. That is a true wave, just like a transverse wave. It's just not what we often think of. And in fact, this models sound waves because sound waves are areas where we have compressed air, in this case, if you're listening to it in air. So that models sound waves really well. All right, now let's just look at wavelength. You can choose a spot on your wave, and when you get to the same spot, you call that one wave. That's your one wavelength. So for example, they chose troughs here, which a trough is the bottom, the crest is the top of the wave. So right here, from this spot, if we go to the next place where it's down low like that, to here, that's one wavelength. You can do the same, and it should be the exact same measurement. You can do it from the top. You can say from here over to here is one wavelength. As long as you are consistent in where you measure from, you should get the same answer. All right, now let's look at the longitudinal wave up here. You're measuring it from areas of compression. So, and on a longitudinal wave, I find it's always easier to measure from areas of compression. Don't try to measure the uncompressed areas. It just gets sloppy. So you would measure from here to here, and that's one wavelength for a longitudinal wave. All right. Wave speed. This is how fast it's traveling through the medium. So if you're looking at a water wave, how fast does it travel through the water? Where if you start a wave on one side of a lake, how long does it take to get to the other side of the lake? And when we look at wave speed, the speed of sound is 330 meters per second. The speed of light is 3 times 10 to the 8th meters per second. So you can see there is a factor there that light is much faster than sound. And the classic example of the speed of light versus the speed of sound is lightning and thunder. When you see the lightning, you can count how far away it is by counting until you hear the thunder. And the reason is that the light reaches your eyes almost instantaneously, but the sound travels much slower and doesn't reach your ears, for 1 or 2 or 3 or 4 seconds, depending on how far away you are. All right, tsunami waves. Now, these are really big waves, but it is still just a wave. These are large amounts of water, and it's traveling very, very rapidly. And usually what causes it is an earthquake, and some of the big ones, the big one we recently had like 5 years ago, was actually caused by an underwater landslide. A chunk fell underwater due to an earthquake, but it was a landslide that actually pushed quite a large amount of water across the ocean. And yes, these are very, very, very dangerous. They move very rapidly and they have a large amount of energy in them. All right, wave relation. So as we look at waves, we have the wave speed, we have the wavelength, and the frequency. And you want to know how they're related. Well, the wave speed is multiplied the wavelength times the frequency. And the way I think of wave speed being the wavelength times the frequency is I think of different animals walking. And I don't know why I think of it this way, but it works for me. I imagine the wavelength being the length of somebody's step, and the frequency is just how fast they're stepping, right? Somebody with very long legs, somebody with a very long sort of wavelength will move at a certain speed as they walk with a sort of slow frequency. But if you have shorter legs, if you're a little kid trying to keep up with your mom, the wavelength of those steps is much shorter, right? It's a smaller wavelength. That little kid has to go with a higher frequency to keep up with their mother. Or you think of a giraffe walking, that would be a very long wavelength. The frequency could be kind of low and mellow because they're taking very long steps. But like one of those little dogs, those little wiener dogs or whatever, they would have a very short wavelength. They have very short legs. And so they have to walk really fast to have the exact same speed, all right? That's how in my head I think wavelength times frequency. This is how it's related mathematically. The wave speed is the wavelength times the frequency. And so if you did the algebra, you could find wavelength is wave speed over frequency, and frequency then is wave speed over wavelength. This top formula is the one I always use, and then I plug in from there. This is the one that you need to have sort of at the top of your page, and this is the one you'll need to remember. All right, what is the wavelength? Okay, didn't ask for the speed, I'm just asking for the wavelength on this one. So, what do you think it is? All right, obvious, 2 meters, right? Wavelength, 2 meters down here. It asks for the wavelength, so that's going to be from here to here. The speed, how fast it's moving, is this. The speed of the wave is it's moving 6 meters per second this direction. But the length is 2 meters from here to here. We could also find it will be 2 meters from here to here. That would be the exact same measurement. Okay. What is the wave speed? That's the 6 meters per second I gave you. And what is the frequency? Well, now you have the speed, right? Speed of the wave equals the wavelength times the frequency. So what number is missing there? You got the speed of the wave is 6. The wavelength is 2. 2 times what equals 6. And then you can find the wave frequency. All right, what's the period of the wave? And remember, the period of the wave is an inverse of the frequency. So once you have found the frequency, you take the inverse and you will get the period. All right, let's look at hearing sound, because hearing sound is one of the waves. And humans can hear very low sounds. 20 hertz is a very low sound, and fairly high sound, not as high as a dog, but we can hear up to 20,000 hertz. The wave speed for sound, we already said 330 meters per second. So if you wanted to think of a wavelength for a very low sound, something that's 20 hertz, it's about 16 meters. That is the distance between these areas of compressed air, 16 meters apart. Very far apart, very long wavelength. Then if we look at the wavelength of something that's 20,000 hertz, those areas of compressed air are only 1.6 centimeters, not meters, 1.6 centimeters apart. So that gives you an idea of the variation of sound humans can hear. All right, so here's some other animals. This is just for fun, but take a look at it. Here's some other animals. Bats have very high frequency hearing. Humans, you see we have a decent range. We're at the bottom there. Cats can hear a little more high frequency than us. Dogs, we know the dog whistle, right, is a higher frequency than the humans can hear. And then we have animals that hear a lower frequency or hear low frequencies. Who knew a goldfish could hear low frequencies? Not me, but anyway, kind of interesting. All right, so let's look at how waves interfere with each other. This is called constructive interference, and this is when we have two waves and we're going to add these together. This is like kind of like math for waves. All right, here we go. We have two waves, and as you look at the waves, you're going to realize they're going the same direction. The crest here and the crest here are going to add and become even bigger. This happens in the ocean. Sometimes you have two waves meet and the wave becomes even bigger. It kind of adds to itself, and the trough here and the trough up here add, and you get a really deep trough. So this is what we add together over here. We're just adding these two waves together. Constructive interference means they're going the same way. You have the exact same phase. It's called a phase. And it means that the crest and the trough are together, and as they reinforce, you get a bigger wave. That's exactly what happens. So for sound, this means it would be louder. For light, it means it would be brighter. For an ocean wave, this means it would be a bigger wave. That's constructive interference. Two waves hit, and they come together to form a bigger wave. All right, now we have destructive interference. This is going to be the opposite of the last slide we just saw. You have, in this case, you have the crest here, but it is coming together with a trough. And so they cancel out, right? This crest and this trough cancel each other. And this also happens in the ocean. Sometimes you'll see these two waves come together kind of at angles usually. It's not like they go head on in the ocean. But as they come to the beach, the shape of the beach, you can actually get two waves coming at angles towards each other, towards one area, and you actually see sort of like this random flat area, and you think, what the heck? You just had two waves crash together and it looks smoother? Well, if they do a destructive interference, you get cancellation. And in sound, you would hear nothing here. This is your noise canceling headphones. It's just destructive interference. They take this trough and this crest, and they just add these two together, and you end up with silence. All right, let's look at waves, transverse and longitudinal waves that are in phase, and transverse and longitudinal waves that are out of phase. For in phase, we would also call that constructive interference, and for out of phase, we would call that destructive interference. So A up here, this is a transverse wave, and it is constructively interfering. You can see the crest is the same here. And so when they combine, you just get a bigger transverse wave. All right, let's do the same thing for a longitudinal wave. This would be an example of a sound wave. You can see areas of compressed air. Remember, these are vibrating back and forth. This is not like wind. Do not confuse sound waves with wind, like somebody blowing on you or something when they're speaking. The wave actually travels by these moving back and forth. This air molecule doesn't like shoot over here and reach your ear or something like that. It's just bumping into its neighboring air molecule. Think of the wave going around the stadium and the fact that the people didn't all run around the stadium, right? Nope, they just stood up and sat back down, but the wave continues. So here we have an area of sound wave, compressed air essentially. And if we add it with another area of compressed air, you will get more compression in this area. This will be heard by you as a louder wave. You have more of this energy, more of the molecules hitting your eardrum. As they vibrate back and forth, they're going to vibrate more and more of these. You're going to get a louder sound. You can see that this area of compression is greater, and the area where it's not compressed there's less molecules there. So they've actually bunched up into this area of compression, all right? And so that is a constructive interference, right? We added this to this over here. These two parts got added together, right here, added to right here, and then this part added to this part, and we ended up with something much louder over here. All right, Now let's look at what happens if we're out of phase. This is also called destructive interference. We're going to add the top to the bottom, and here's one wave going up and down, and it's added to this wave going up and down, and what we would have here is nothing. All right, flat, silence, nothing. We do that for sound. Here we have an area of destructive interference, This area of compression is going to fill in essentially this area where it's not compressed, all right? And so as we fill in, we just end up with nothing over here. This is just regular air, no sounds moving through it, nothing's going on there. So, I'm not doing this demo for you, but you can imagine two pairs of speakers, and they can constructively interfere and make something sound louder, and they can destructively interfere and make something sound quieter. Now, the key here is, as things bounce around, usually at certain notes will be constructively interfering and louder, and you will just lose other notes, and so it just doesn't sound as good. And you'll notice a lot of, where you have concerts and stuff, they try to dampen the reflective sound. They put curtains up, they put, that egg crate stuff up, and that's because they don't want extra sound bouncing around and being in phase or out of phase. All right, how do your noise canceling headphones work? Well, they make noise, and they make it specifically out of phase of whatever noise they're picking up outside. So if they pick up an external noise, they make the destructive wave to interfere with it, which again is silence, and then you can hear whatever you wanted to hear. All right, so let's look at standing waves in phase. What a standing wave is it's not a moving wave. It's a wave that you're shaking like a rope attached to a wall. The wave is not going anywhere. But we can do the exact same thing with the wave. We can have it constructively interfere or destructively interfere, right? So it's just how you shake it. And if you shake the wave correctly, you can get sort of your rope going up and down. And if you shake it kind of spastically, you're going to end up with interference. Doppler effect. I love the Doppler effect. This is why the sound sounds higher as the siren comes towards you. It goes, when it's going wee-oo, wee-oo. As it comes towards you, you can hear it sounds higher, and then as it passes you, it goes lower. It goes wee-oo, 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 right? Or when you're at the racetrack, you hear the cars go, and you can hear as they come towards you, it sounds like a higher pitch, and as they go away from you, it's a lower pitch. Why? Why does that happen? Well, the source of the sound is moving, and as it moves towards you, each time it emits this sound, it is moving and compressing the wavelengths in front of it. It's actually moving into its own wavelengths and making the new sound, and so they become shorter. So here we have the source of the sound, and it's moving this direction. These are the waves. Imagine these lines being the wave crests. As this emits the sound, it now emits the sound over here, and it compresses these. It's not compressing them, it's actually emitting the sound in a new location where these end up getting bunched up, and it's driving away from these sound waves. So it made this sound wave probably when the truck was here, right? Well, the next sound wave it's going to make that's going to go backwards this direction, the truck's going to be way over here. And so these end up being farther apart, right? You see the waves behind it are farther apart, and the waves in front of it are closer together. And that is the Doppler effect. All right. Yeah, so now you can just see the truck's moved away, and you can see it has made those wavelengths, and they're farther apart from the backside. Okay, demo, Doppler shift. I do not have this, so I will not be doing it, but if you take anything that emits a sound and you spin it as it flies towards you, you get a shorter wavelength, and as it goes away from you, it's a longer wavelength, and so you'll hear a higher pitch as it goes towards you, lower pitch as it goes away from you.